So, welcome to this class on hardware security. So, we shall be continuing with our discussions on elliptic curve cryptography. So, today we shall be starting with a definition which we did not cover in the last class, which was on what is called as singularity of elliptic curve. As I say that the elliptic curves are typically non-singular, and then we shall be going into what is called as scalar multiplications, which is essentially the cornerstone of elliptic curve cryptography, and we will try to see various approaches of obtaining these elliptic curve operations. So, we shall be trying to look into some techniques which are called as say Montgomery techniques, like some very interesting techniques of how you can operate with only x coordinates. You do not need the y coordinates for doing your computations. Okay. And we shall be subsequently looking into a transformation which is called as projective coordinates. The objective is to reduce the complex inversions which are often required in this kind of operations, and we shall be taking a quick look into what is called as mixed coordinate systems. And finally, we shall be trying to look into some parallelization techniques and how we can parallelize the Montgomery ladder, which can be utilized for efficient architectures. So, let me quickly define what is called a singularity of an elliptic curve. So, for an elliptic curve, say y squared equal to f x defined. So, like you can write a function f x comma y as y squared minus f x. Okay. So, a singularity of the elliptic curve is at a point x 0 y 0 if its partial derivative with respect to x and partial derivative with respect to y both vanishes. Okay. That means, del f del x with x 0 y 0 at the point x 0 y 0 is equal to del f del y at the point x 0 y 0, both are equal to 0. Okay. So, if you take this equation, therefore, if you derivate it with respect to say x, okay, then you get minus like you get minus f dash x 0. So, you get minus f dash x 0, and likewise, right, if you take 2 so this will be f x comma y equal to y square minus small f x. Okay. So, please correct this is y square minus small f x. Okay. So, that means, right, what I mean to say is that this is y square minus f x, okay, small f x. So, then if I derivate this with respect to y, then I get 2 y, okay, and if I derive this with respect to x, then that means equal to minus f dash x. Okay. And if I plug in the point x 0 comma y 0, then that means 2 y 0 is equal to minus f dash x 0. Okay. So, now you can easily verify, therefore, that that means that 2 y 0 is equal to 0, which means y 0 is equal to 0, that means f x 0 is equal to 0, and likewise f dash x 0 is equal to 0. So, that means the curve has a double root at the point x. Okay. So, it has got a double root, that means it also itself satisfies the curve, and it also satisfies this differential equation. Okay. So, it is usual to assume that the elliptic curve has no singular points, okay, and therefore, we consider non-singular curves in our discussion. So, therefore, right, let us try to kind of like similarly kind of derive like the criteria, which is essentially what we have for such kind of okay, let me clear this. Okay. So, therefore, right, if I for example, like if I take my equation as y squared equal to x cube plus ax plus b, and I want to essentially like derive the criteria for which this will be a non-singular curve. Okay. So, this is often related to what is called as a discriminant of the curve. Okay. And the discriminant in this case is 4a cube plus 27b squared. If this is not equal to 0, then this implies that there is no singularity in the curve. You can easily derive it. So, as I said, that it means that there are no double roots. So, therefore, if I take the curve like x cube plus ax plus b equal to like, and if I like since it has got no double roots, that means for double root it would mean that this is equal to 0, and likewise the derivative with respect to x, which is 3x squared plus a, that is also equal to 0. So, if 3x squared plus a is equal to 0, which means x square is nothing but minus a by 3. Okay. So, now if you take this equation x cube plus ax plus b equal to 0, and if I multiply x on both sides, then I get x to the power of 4 plus ax squared plus bx equal to 0. X to the power of 4, therefore, you can write as x squared squared, that means minus a by 3 whole square, which is a squared by 9, and x squared you can substitute by minus a by 3. So, you get minus a squared by 3 plus bx equal to 0. So, therefore, you obtain that x is equal to 2a squared by 9b. Okay. So, you can just do a few arrangements and you will get x equal to 2a squared by 9b. So, now if you take this equation 2a squared by 9b, and you know that since you have got this equation, that is like 3x square is equal to minus a, that means 3x square plus a is equal to 0. So, therefore, you will get 3 into 2a square by 9b whole square plus a is equal to 0, and from there you can get this criteria, which is 4a cube plus 27b square is equal to 0. That means, for singularity you need to have this discriminant is equal to 0. For non-singularity, this means that this should not be equal to 0. Okay. So, typically we consider elliptic curves which has got no singularity in them, okay, because apparently, right, that makes the discrete log problem more hard, okay, and that is essentially what we require for our public key cryptography. Okay. So, now, right, I mean we will be more focusing on elliptic curves in characteristic 2. Again, we can start with our original Weierstrass equation, and you can see that with few simplifications, like for example, if a1 is this coefficient is not 0, then this reduces to the form y squared plus xy equal to x cube plus ax squared plus b. Again, I am not going to the derivations, but you can take it and you can also try it yourself. And likewise, if a1 is 0, then this reduced form is y squared plus ay equal to x cube plus bx plus c. So, you can see that there are small differences in the form of the equations, but nevertheless all these forms are much more simple compared to the original Weierstrass equations, and therefore, depending upon the cases, these are often used for doing computations. Likewise, right, and also note that it is very important to note that this equation cannot be of this form, like y squared equal to x cube plus ax plus b, because if you remember that when we derive this, we assume that the characteristic was not 2, okay, and therefore, right, we get curves of different nature compared to this, okay. But nevertheless, they are also, like still having the same like same nature. That means it is quadratic still with y and cubic still with respect to x. Okay. So, now we were all set to understand how the elliptic curve operations are done. So, the elliptic curve essentially you can imagine is kind of a pyramid. Okay. So, you have got finite field operations at the bottom, where you are doing your multiplications, additions and field inversions. On that you define your group, on which the group operations are the chord and tangent rule that we saw. So, we saw how to add 2 points p and q. If the point p and q are same, then I add p with p. So, in that case we draw a tangent at that point, and that essentially is often called as a doubling operation, because you are adding p with p. So, you are getting 2p, that is the doubling operation. Okay. So, you can define your addition, you can define your doubling. And now, with addition and doubling, you are all set to compute what is called as a scalar multiplication. Okay. So, in scalar multiplication, very simply put, you essentially do this operation. So, you basically calculate. So, this is your Kp. Okay. So, here this is often called as the scalar multiplication. So, this is often called as the scalar multiplication. So, scalar multiplication often implies that you are adding, you are adding say the point p k times. Okay. So, if you are adding to the point p k times, that implies that you can also of course that can lead to a very inefficient operation. So, there are techniques of how you can make it more efficient. Okay. That means how you can make the scalar multiplication more efficient. That means you can make them work in reasonable amount of time and also consuming reasonable amount of resources. Okay. So, that is essentially the sort of main theme of today's discussion, how you can do the scalar multiplication in an efficient manner, and subsequently what we will see is that how you can make a corresponding hardware architecture for realizing the scalar multiplication operation. Okay. And on this, right, your elliptic curve cryptography is kind of dependent. So, we will not be really looking into the ECC part, where there are several versions. You have got Elgamal crypto systems, you can apply elliptic curve for key exchanges, which are often called as a Diffie-Hellman key exchange. Okay. But all of them, right, fundamentally uses this scalar multiplication. So, the scalar, so whenever we talk about an elliptic curve processor, it means that there is a hardware unit which is essentially able to do this scalar multiplication. Okay. So, therefore, the entire focus is in making this scalar multiplication more efficient. So, let us try to see therefore how we can obtain this scalar multiplication in a more efficient manner. So, there are some techniques of doing this. Okay. The easiest thing to see is that what is called as double and add algorithm, but the double and add algorithm operates from the MSB. Okay. So, what essentially is done here is we take what we do is that we take the scalar, the scalar is k. So, this k is called as the scalar. Okay. So, this is the scalar which is essentially referred in the scalar multiplication, and we write that in a binary format. So, we write that in the binary format. So, that means all of these values k0, k1 till km minus 1 are nothing but either 0 or 1 in this case. So, now I want to calculate q equal to kp. Okay. So, I want to basically add p k times. Okay. But now what I will try to do is that I will try to process it from the MSB. So, this is your maximum significant bit. So, we try to operate it from this side. Okay. So, note that we will assume that in this expansion the previous term, that is km, is implicitly 1. Okay. So, we try to process it from m minus 1. So, therefore, right, so basically, right, I mean what we will first look is in a scalar multiplication algorithm where we expand the scalar. So, the scalar is in this case like this term, that is the variable k, okay, and we essentially are so this is your scalar k. That means this k is essentially often referred to as a scalar, and here we kind of expand this in this binary format. So, that means k minus 1 till k0, that means we have used m bits to represent k, okay, and all of these terms like k0, k1 till k minus 1, they are either 0 or 1. So, basically the binary expansion of k. So, note that k minus 1 is 1, that means this term is essentially 1. Okay. So, this term is implicitly assumed to be 1 in this case. Okay. So, now when we are processing, so when we say MSB first, that means maximum significant bit first, it implies that we are processing from the left. Okay. So, this is also called as the left to right scalar multiplication. So, the algorithm is very simple. So, what we want to do is basically add p k times, but without explicitly doing so. So, what we do now is that we initialize q to p, okay, and then from m minus 2, note that I know that k minus 1 is 1. So, I start processing from m minus 2 and I start to do always a doubling operation, and I do a conditional addition depending upon the fact that whether this ki bit is 1 or not. Okay. That means, if ki is equal to 1, okay, if ki is equal to 1, then I do a conditional addition, that is q equal to q plus p, and finally I return q as the result. Okay. So, you can easily verify that this answer will be correct. Okay. That means, you will get correct result, but before I go into that, you can observe that this is a sequential algorithm, because we are like processing one after the other, and it will typically require m point doubling operations, because you are always doing a doubling operation. But if you assume that on the average half of these terms are 1 and half of them are 0, then you are doing half number of additions. Okay. You are not doing m number of additions, but probably you are doing m minus 1 by 2 number of point additions. Okay. So, on an average. Okay. Sometimes you may do all I mean, if it is all 1, then you have to add always, and likewise if it is all 0, then you have to probably add even less, but on an average, right, you should be a kind of half number of additions that you have to do. So, therefore, right, I mean this algorithm is correct, you can easily verify this. So, suppose I want to calculate 7p. So, 7 can be written as 1 1 1. So, note that if I leave out the first 1 and I start processing from this one, okay, that means like I will do like a 2 into p plus p, okay, that is because of it is 1, and likewise since the second bit is also 1, I again do 2 into that plus p. Okay. So, then you can see that this is 2p plus p, which is 3p, into 2 is 6p, plus p is 7p. Okay. So, you note that 2 iterations are required, and I first do a double and then I do an add. So, that is the basic principle of this technique. If I likewise want to calculate 6p, so 6p is 1 1 0. So, here because of this 1, I will do a 2 into p plus p, but since this is 0, I now only do a doubling, but I do not do an addition. Okay. So, therefore, I get 2p plus p is 3p, into 2 is 6p. Okay. So, you can also write likewise, this is very simple, you can do it pretty simply, but there are like some variations of this also, which we will very soon see. For example, you can also do it from the right. This is called as a right to left scalar multiplication. So, if I start processing from the right, that means I start processing from this side, okay, and essentially I am starting to process from the LSB in that case. Okay. So, in this kind of algorithms or in these variations, right, we basically have got two registers. We have got a register Q and a register R, and now I initialize Q to 0 and R to P. Okay. So, now what I do is that if Ki is 1, then I do a Q plus R, that means I add these two registers and I store the value in Q, else I only do a doubling in R. Okay. I only do a doubling operation in R. I mean rather I do a doubling operation always. Okay, so this is exactly similar as the previous one. That means I am always doing a doubling, but the doubling is done in the register R. Okay, but the addition is being done in the register Q, but the addition is done in a conditional way. That means if your secret bit is 1, only then you are doing the addition operation. Okay. So there are certain small points here. For example, you can parallelize it. Okay, that means since the accumulation, that means addition and doubling are done in separate registers, you can pretty much parallelize, like if you have got resources, of course, you can parallelize the accumulation and the doubling operation. The addition and the doubling can be parallelized, which means like since we will see that addition is more complex than doubling operation, the latency will be that of course, that of the addition operation. Okay. So therefore, right, on an average, you can imagine that there will be m by 2 point additions and m by 2 point doublings. Okay. So note that here also you are actually doing m doubling operations. Okay. But then why do I write m by 2 point doublings? I am writing because of the assumption that they are parallelized. Okay. So if they are parallelized, right, then whenever I am doing addition, then of course the cost is that of an addition operation, but on the other cases it is only the doubling operation which is coming into play. Okay. So with that assumption, right, you can essentially and the important point is that if you pay this resource, that means 2 registers, few more computations in parallel, then there is a scope of parallelism in the algorithm. Okay, although it is a sequential algorithm, the nice thing is that there is a scope of parallelism in the algorithm. Okay. So now, right, I mean we can essentially look at the correctness of this equation. Again, let us take 7p and 6p as an example. So again, I am processing now from the right side. So I initialize q to 0 and r to p. Note that this is 1. So I add q with q plus r. So I get 0 plus p, which is p, and I double r. So I get 2r here. That means 2p. Okay. Again, the next bit is 1. Okay. So the next bit is 1, which means I add in q. That means I add p with 2p. So I get 3p. And since it is 1, I also do it. I do a doubling operation always. So I calculate from 2p. I calculate 4p. The next bit is again 1. So note that here I have to go for all the 3 bits actually. Okay. So therefore here it is 1. So I add 3p with 4p. I get 7p, and I always do a doubling. So I get 4p into 8p. But this is not useful here because my result is already computed in 7p. Okay. This is required if I have got further more things or inputs to process. Okay. Likewise, consider 110 case. So in this case, right, I get a 0. So I don't do anything in q. There is no addition being done. Of course, I have to do a doubling because doubling is always doubling, because these are all always double algorithms. So I double r, I get 2p. Next time I have got a 1 here. So I again add with q with p with 2p here. So I get 2p in q. I double r, I get 4p. And in the next iteration, I add 2p with 4p. So I get 6p. So 6p is my result. Okay. So right, I mean, so now if we compare say 31p, which is the slightly bigger example, and compare these two algorithms, MSB first and LSB first. So you can see here there are more steps which are required. Okay. So you are doing q equal to 2p, then so when I am doing MSB first, I am processing from this one. Okay. So I am getting a q equal to 2p, then I am doing a q equal to 3p, then I am doing 6p, 7p, 14p, 15p, 30p and 31p. But when you are doing LSB first, you see that you can do the addition and doubling in parallel. So if you can do them in parallel, then you can do it in lesser number of clock cycles, okay, or lesser number of steps. But both of them will give you the correct result, and therefore your choice, right, essentially can be influenced depending upon the context. Okay. There can be more implications also about this, but at least this is what we see at this point. Okay. So now we want to basically consider in particular curves of characteristic 2. So that suppose I assume that I have got this equation y squared plus xy equal to x cube plus ax squared plus b. So this is my curve equation, and I want to essentially do my arithmetic where x comma y, that means the point on the curve belongs to the gf2 power of m cross gf2 power of m field. Okay. So now let p equal to x1 comma y1 be a point on the curve. The first thing to observe here is that minus p is slightly different from what we have seen previously. Okay. So minus p is x1 comma x1 plus y1. Okay. Why does it happen? So you can easily see this, why it works so. So if I take the point, for example, I take this equation, say y squared plus xy equal to ax squared plus b. and consider, so the idea will be the same. That means, I have got my elliptic curve in this way. So, imagine that this is my elliptic curve, and I will basically draw a straight line like this. Okay. So, this straight line is say x equal to h. Okay. So, now if this is my point like x1 comma y1, I consider this point as a negation of p. So, if this is p, then if this point is p, then this point is minus p. Okay. So, that means, I will take this line x equal to h and I will intersect in this curve. Okay. So, if I do that, then I will get y squared plus x will be h. So, I get hy. Remember that is a characteristic 2 field. So, I can bring this in this side, but that is okay, I do not read it. So, finally, I get this is equal to 0. Okay. So, now there are so we can observe that there are two equations here. So, one of them is say y1, okay. The other one is say y1 dash. Okay. So, y1 dash is what we want to compute. So, this if I add will be the negation of h, but since this is characteristic 2, this will be equal to h. Okay. So, this implies that y1 dash is equal to h plus y1. Okay. So, h here is x1. So, if it is x1, then I get x1 plus y1. Okay. Of course, the x coordinate remains the same. So, that means the minus p in this case is x1 comma x1 plus y1. Okay. This is the first thing to observe. So, likewise, there are certain other things also which are slightly different compared to what we have seen, but essentially the ideas or the principle is still the same. So, you can essentially derive the addition equations and you can derive the doubling equations. Okay. It is interesting to see how we can draw the doubling equation. So, let me try to concentrate on that. So, let me try to kind of derive this equation. So, suppose I have got my equation as y square. So, this is my equation, right, y square plus xy equal to x cube plus ax square plus b, where x comma y all are elements in GF 2 power of m cross GF 2 power of m. Okay. So, now I want to obtain the doubling equation, because that is of particular importance to me. Okay. So, here what I do is I derivate this as previously, but remember that these are characteristic 2 fields. Okay. So, therefore, right, when I write 2y dy by dx, right, then this 2 is actually equal to 0 in this field. Okay. So, but let me continue that. So, if I write 2y dy by dx plus I derive this, right. So, therefore, I write I derivate this. So, I write here x, okay, and dy by dx plus y. Okay. This is equal to 3x square. So, first I am just writing in a very naive way 2x. Okay. So, now if I put in the fact that I have got characteristic 2, so I will do modulo 2 of the coefficients. So, with that, right, this is equivalent to saying that this x dy by dx plus y is equal to x square plus 0. So, therefore, I got just x square. Okay. So, that means dy by dx, okay, is equal to x square plus y by x. Okay. So, if I now do this at the point x1 comma y1, so that means it is x1 squared plus y1 divided by x1. Okay. So, now if you take again apply the same cordon tangent rule, that means you have got your elliptic curve and you want to calculate the doubling say at the point P, that means you draw your tangent at this point. Okay. So, if you want to do this, then I mean that you have got your equation as y equal to mx plus c, where m is obtained in this fashion. So, this is your m, right, m of the slope of the curve of slope of the tangent. Okay. So, this is the tangent. Okay. So, therefore, right, if I do this, therefore, if I plug in this into this equation, then I get mx plus c whole square, okay, plus x into mx plus c equal to x cube plus ax square plus b. Okay. So, if I arrange this term, then that means like this would imply that I bring x cube here, and if I obtain the coefficients of x square, then I will have m square plus m, okay, plus a, okay, plus other things which I do not require here, and is equal to 0. So, now you see that I have got the points say x 1. So, suppose x is x 1 comma y 1. So, now you have got 2 x 1 because x 1 plus x 1 plus the point which you want here. So, suppose this is your x 3 dash, okay, and this is equal to m squared plus m plus a. Okay. Again note that this is equal to 0 here. Okay. So, therefore, this will vanish, and therefore, right, you have got I can take this space to write that x 3 dash, right, x 3 dash will be equal to x 1 squared plus y 1 divided by x 1 whole square plus x 1 square plus y 1 divided by x 1 plus a. This is your x 3 dash. Okay. So, this, right, essentially turns out that if you do a little bit of simplification, you will get the denominator as x 1 square, and the numerator is x 1 to the power of 4 plus y 1 square plus x 1. So, I have to multiply this. So, I will get x 1 cube plus x 1 y 1 plus a x 1 square, right. So, now you can observe that since x 1 comma y 1 is a point on the curve, okay, so you can note here that this is a note that x 1 comma y 1 is a point on the curve, and therefore, I will have y 1 squared plus x 1 y 1 is equal to x 1 cube plus a x 1 squared plus b. Okay. So, that means y 1 squared plus x 1 cube plus x 1 y 1 plus a x 1 squared. Okay. This you can write as nothing but x 1 to the power of 4 plus b by x 1 squared. Okay. So, now you see that there is no y in this equation. Okay. This doubling, right, essentially is nothing but x 1 squared plus b by x 1 squared. Okay. And therefore, you have completely eliminated y from this equation. Okay. So, this is the first thing to observe, that there is a nice property where you only have x involved. Okay. So, now with this setup, right, we can essentially try to like get back and understand what is the implication of this. So, the first implication is that you do not require any y for doing the doubling. Okay. But of course, right, for x, I mean for the addition where p and q are not the same, you still need y. Okay. And now what we will see is a method which is due to what is called as a Montgomery ladder, okay, which says that you can still do the addition operation by a trick which is called as a Montgomery ladder trick, where you don't still need to compute or store the y coordinate. Okay. Before I go into that, you can observe here that for point addition and doubling, both require one inversion and two multiplications. Okay. So, for example, here you see that I need to calculate 1 by x 1, that is one inversion, and I need to obtain to perform two multiplications. Why? Because I have to multiply by y 1, that is one multiplication, and also I need to multiply with x 3, that is my second multiplication. Note that I am neglecting the operations due to squaring and multiplications with constants, because for them I do not need a dedicated multiplier. Okay. When I am doing multiplication with a constant, I can optimize it. When I am doing a squaring operation, also we have seen it is much more simple, and in fact, there are some basis representation like the normal basis, whereas squaring is nothing but a rotation. So, you can essentially do it quite simply. Okay. But likewise, for the addition operation, you have to do 1 by x 1 plus x 2, which is one inversion. Again, you have to do a multiplication because you have to multiply with y 1 plus y 2, and you have to also multiply with x 1 plus x 3. So, here it seems that both of them, like addition and doubling, both requires one inversion and two multiplication operations. That is the cost. Okay. So, what we will see in the next class is like how we can optimize this and how you can perform the Montgomery's ladder trick, so that you can do the addition still without storing the y coordinates in the next class. So, thank you for your attention.